All right, let's go ahead and talk about polar covalent bonds. Now, covalent bonds, again, have to do with the sharing of electrons. But if you remember from last unit, we talked about this trend called electronegativity. And what electronegativity is, it is the pull on shared electrons. And so now what we're going to do is we're going to think about how when two elements come together and they share their electrons, they might not share them equally. And so let's go ahead and have a quick reminder about what electronegativity is. Look at the chart here. Notice how electronegativity increases going up and it increases going to the right. And again, the reason why that is because as you go up, the electrons get closer to the nucleus because of fewer energy levels. And as you go to the right, there's an increase in protons, which increases the attraction that the nucleus has on to the electrons. And so notice how the most electronegative element is fluorine, and notice how generally the upper right corner of the periodic table is very electronegative. Also notice how the first three noble gases do not have any electronegativity, and that's because noble gases tend to not share their electrons, but we will learn in another Edpuzzle coming up here that krypton can share its electrons and xenon can share its electrons as well, and that's why they do have a certain amount of electronegativity. And so we'll talk about why they're able to do that in the future video. But something else I really want to point out is, remember, we want to keep in mind that a covalent bond is between two nonmetals. So two of these will make a covalent bond, compared to an ionic bond, which is a metal and a nonmetal. All right, so let's keep in mind that covalent compounds are two of those. So keeping this chart in mind, again, these electronegativity is the pull on shared electrons. Let's go ahead and keep in mind the general trend there. So covalent bonding can be either polar or nonpolar, and we're going to talk about what polarity means. And it's dependent on the strength of the attraction of each atom for the shared electrons. Now, a nonpolar covalent bond is one in which the electrons are shared equally between the two atoms. So think about if we had, let's say, two fluorine atoms. If we had two fluorine atoms, they both pull on the shared electrons equally. And so that is going to be a nonpolar bond. And so we'll talk about what a polar bond is in a moment here. But imagine a fluorine atom and let's say a phosphorus atom. Let's say those two are sharing electrons. Well, phosphorus has a lower electronegativity, and so what ends up happening is fluorine pulls harder on those electrons. And so generally speaking, nonpolar covalent bonds occur between atoms with the electronegativity difference of 0 to 0.4. So if you have two elements and their electronegativities are within 0.4 of each other, we're going to consider that to be equally shared electrons. Now, if you take a look here, let's take a look at oxygen and fluorine, for example. Look at the difference between the two. And if you see the difference there, that actually is about 0.44. And so that actually won't be considered, it's like right on the boundary of being nonpolar or polar. But maybe consider carbon and phosphorus. So if you take a look at carbon and phosphorus, the difference in electronegativity is less than 0.4. And so carbon and phosphorus are going to tend to make a nonpolar bond. Look at sulfur and bromine. Those are pretty close to a nonpolar bond as well. You can look at selenium and iodine. You can look at bromine and xenon. And so those are going to tend to be nonpolar bonds. And that's because their electronegativities are pretty close to each other. Now, a polar covalent bond is a covalent bond in which the bonded atoms have an unequal attraction for the shared electrons. And so what ends up happening in a polar bond is one atom is going to be more electronegative than the other, and so it's going to pull on those electrons more. And because it pulls on those electrons more, it's going to pull those negative electrons closer to itself. Now, generally speaking, anything between 0.5 and 1.7 is going to be a polar bond. And so if you have an electronegativity difference between 0.5 and 1.7, you're going to make a polar bond. And so take a nitrogen and fluorine, that is a 0.94 difference, so that would make a polar bond. Look at nitrogen and phosphorus. So nitrogen and phosphorus will make a polar bond as well. Fluorine and chlorine will make a polar bond because those are within that 0.4 to 1.7 range. And then also look at hydrogen. Hydrogen's 2.2. Hydrogen makes covalent bonds with all of those nonmetals, and so hydrogen will make a very polar bond with oxygen and fluorine and chlorine, and that's going to be important later. It'll be a very polar bond with nitrogen as well. So important later. Now, a dipole is used to represent this unequal sharing of electrons. And so what ends up happening is when an atom is pulling hard on those electrons, it's sort of pulling those negative electrons closer to itself. And what happens is that atom becomes partially negative, and the electrons that, or the atom that has electrons being pulled away from it, becomes partially positive. And so what you end up with is this bond in which there's a partial negative side to it and a partial positive side, and we can represent that uneven sharing of electrons with a dipole. And a dipole is represented by an arrow with the head pointed towards the negative pole, and then you cross the tail at the positive pole, so it kind of makes a positive sign. And so if you take a look here, this is an example of a dipole. So look at the H and the F. Hydrogen and fluorine make a very polar bond because fluorine is very electronegative. And so what happens is fluorine pulls those negative electrons closer to itself, and it becomes a partial negative. Now notice the symbol above fluorine. That is a delta negative. It's a little delta negative. And so that symbol represents partial, the concept of a partial. So it is a partial negative. Now, what would it take for it to be a full negative? For it to be a full negative, fluorine would have to completely pull those electrons away. And so that is what an ionic bond is. However, in this situation, hydrogen is still sharing, our fluorine still is sharing the electrons with hydrogen. It's just pulling those electrons closer to itself. Now, again, because those electrons are being pulled away from hydrogen, hydrogen becomes a partial positive, but it's not a full positive because it's still sharing those electrons. Now, I want you to take a look at the blue bonds above. A non-polar covalent bond is where there's equal sharings, the electronegativity is similar, and so the electrons are evenly shared throughout. And then look at the polar covalent bond where we have the partial negative and partial positive. And then if we end up with a very large difference in electronegativity, that's where an ionic bond occurs, where the atom is so electronegative compared to the other one that it completely removes the electron, which makes sense because these over here tend to have low electronegativity. So metals tend to have low electronegativities, which is why non-metals, which have high electronegativities, are able to completely take away those electrons. And so that's where this last part is. Bonding between atoms with electronegativity differences that are greater than 1.7 are considered to be ionic bonds. And so you'll actually, in some situations, see that it's there might be a different cutoff for the 1.7, but generally 1.7 or greater, you have an ionic bond. So as you get a larger difference in electronegativity, that's where you're going to get elements that are completely removing those electrons. And so think about sodium chloride. Let's think about that. So sodium 0.93, chloride 3.16. That is a huge difference in electronegativity, so much so that chlorine completely takes away that electron, and that's where we get an ionic bond occurring. And again, in that situation, it's going to be a full negative for the chlorine and a full positive for the sodium because it's completely removed. That's compared to, let's say, fluorine and chlorine. Both of them are very electronegative. Neither one of them is going to necessarily lose those electrons. They're both going to be pulling on it. Fluorine will pull harder, but the difference is close enough to where fluorine will not completely pull it from chlorine. So the general idea of polar covalent bonds is as you get when you have the sharing of electrons, there might be an uneven sharing of electrons if an element is more electronegative or not. We'll talk more about this in class, and we'll talk about how we can determine if it's polar or not just by looking at the periodic table, because there's a couple tricks you can do. If you have any questions, come with those questions, and I hope you have a great day.